Let's do another example of the second derivative test to find the local mins and local maxes of a function. And so to recap, in order to use this second derivative test, you first have to find the critical values, which always comes from the first derivative. So first step, find the first derivative. Here we'd have 5x to the fourth minus 45x squared by power rule. And then to find the critical values, we always need to set the first derivative equal to 0 and solve. And this is actually my second recording of this video because last time somehow my 4 disappeared and I got the wrong answers and did the whole video without even noticing. But anyways, yes, set the second derivative equal to 0. Make sure you copy everything down correctly to find the critical values. And now, again, we have a polynomial equation equal to 0. We need to factor. So we have a common factor of 5x squared. This would leave us with x squared minus 9. And that being a difference of squares could be factored as x plus 1 and x minus 1. Sorry, x plus 3 and x minus 3. This is x squared minus 9 is what we have remaining after factoring out 5x squared. And this leaves us with 3 solutions to the equation or 3 critical values. So 0, -3, and +3 all would be solutions to this equation. And we have our critical values. Cool. So again, when using the second derivative test, again, we could use the first derivative test. It technically doesn't tell us to use the second derivative test, but I always think that is the easier path. Even though you have to do another derivative, it is way faster because all you need to do is plug your critical values into your first derivative, and that tells you directly whether they're mins or maxes by the sign on that answer. So just to reiterate, second derivative would be 20 x cubed. So I take my first derivative and take the derivative of that. So again, power rule, drop the 4. 4 times 5 is 20, 20x cubed. Then with this 2, drop the power, subtract 1, 2 times 45 would be -90. And again, losing 1 power. So there we have our second derivative. And we don't need to set it equal to 0 either. All we need to do is plug in those critical values. So let's start with -3, start with the smallest. If we plug -3 in, that would give us 20 times -3 to the 3rd power. So let's go ahead and do that. 20 times -3 cubed. And then it would be -90 times -3. Also, we don't really care what the answer is. We just care whether it is positive or negative. So that would be -270. But again, negative indicates concave down. And also remember, concave down, since it looks kind of like that, indicates that the critical value, which is at the top or bottom of that curve, would have to be a maximum. So again, we're going to get at -3, we have a local maximum value on our curve based on the behavior of the second derivative. Now, if we check the second critical value, 0, so we know what that one's going to be. H double prime of 0 would be, well, plugging this into the second derivative, I'd have 0 minus 0 is 0. And also remember from the second derivative test, the little thing at the bottom, if it's 0, then this test is inconclusive, meaning we want to do something else. So here we're not really sure about the concavity. What this is actually indicating is it's neither concave up or down at that point, which typically indicates it's not a min or max, but we need to do a little bit more investigation. So we'll use the first derivative test here in a second to check on that one. And then looking at the last critical value, which was 3, all I got to do is plug that into my second derivative. So if I plug 3 in, this would be the same exact thing I just calculated, but with a +3 instead. And this would leave me with +270 instead of negative. And again, positive second derivative indicates concave up. Concave up looks like this, means that there's a minimum at that point, local min. And again, this is all just the second derivative test, you can always, what I recommend is while you're practicing using it, use the textbook's strategy to help you get started. And remember the generic step-by-step procedure for using these tests. First step, find the critical value. So step 1, first derivative. Step 2, set it equal to 0 and solve. Once you solve your first derivative equal to 0, you get your critical values. Then, to do the second derivative test, you need to find the second derivative and plug them in. I think that's simpler than the first derivative test, but very, very similar at the end of the day. Now, for the position at which we were inconclusive, we still want to figure that out. So we can always revert back to the first derivative test. And remember how that works, kind of like drawing the number line was the way of visualizing the first derivative test. We had our critical value at 0. And if we're using the first derivative test, we want to check, well, what's the behavior to the left and to the right of that critical value? And so basically we can plug in 1, -1 into our first derivative to see if it's positive or negative. Now, if I plug in -1, I'm going to get 5 times 1 minus 45 times 1. So that would be -40, or again, we don't care about the value, we just care about the sign. So this, I'll just write first D test here because I'm kind of swapping to go back and figure out this one that we didn't know from before. What happens when our second derivative is 0? And actually, as I'm going to talk about in the next video, this is what's called an inflection point. And these are often the weirder locations on your function. Now, if we plug in 1, it's actually exactly the same thing as if I plug in -1, I'm going to get 5 minus 45, also negative. And by the first derivative test, remember the logic here is a little different. The first derivative indicates whether the function is decreasing or increasing. So since both of those were negative and a critical value occurred at 0, what it means over here is it was negative and eventually is flattening out for a critical value of 0. And then on the right, it's going back to negative derivative. Again, it's sort of like looks like a little bend in the curve, which is not, remember, when it does not change signs on the first derivative test, that means it is not a relative min or relative max. So sort of summarizing over here, when the second derivative test is inconclusive, we go to the first derivative test instead. Let me just finish sketching that out, which means, by what we did over here, it was neither a min or max at that location. And I should just sort of ignore that critical value. Remember, sometimes critical values happen when you have mins and maxes. Sometimes nothing happens. And at the end of the day, we can figure all of this out without even looking at a graph.